something unusual is happening in the inner solar system right now. An interstellar object named 3I Atlas is no longer just reflecting sunlight, it is glowing gold. In the last few weeks, its color has shifted from green to yellow, a rare transition that may signal internal change or even the early stages of fragmentation. Even more surprising, astronomers detected nickel gas without the iron that normally accompanies it, hinting at a history shaped by intense heating near another star and long exposure to interstellar space. As 3I Atlas approaches Earth on December 19th, under a new moon in Leo, observations are entering a critical window. Stay with us, and if you value clear science updates like this, tap like and subscribe. Now, let's begin. Over the past several days, astronomers around the world have reported a clear and unusual change in the appearance of the interstellar object known as 3I Atlas. Its light has shifted from a green tone to a distinct golden color. This is not something that is commonly observed. Comets, and especially interstellar objects, rarely show a gold-colored glow. Most remain gray, white, or sometimes green when certain gases are active. A sustained golden hue immediately raises questions about changes happening at the surface and within the material being released into space. There is a useful comparison already inside our solar system. The comet, known as C2025 K1 Atlas, showed a similar transition roughly 6 weeks ago. As it moved into the constellation Leo, its color shifted toward gold. Shortly after that change became clear, the comet began to fragment, breaking into multiple pieces. That sequence makes the current behavior of 3I Atlas difficult to ignore. A color change alone does not guarantee fragmentation, but when paired with past examples, it becomes a signal that scientists take seriously. The question is whether this golden glow reflects a new chemical phase, a change in dominant material, or internal stress that may lead to physical breakup as the object continues deeper into the solar system and toward Jupiter. Current evidence suggests that 3I Atlas did not form in isolation. Its physical and chemical traits are consistent with an object that once orbited its original star many times. In other words, it likely behaved as a short-period comet in another star system, over hundreds or possibly thousands of close passes around that star. Its surface would have been repeatedly heated. This process, known as thermal processing, slowly removes lighter ices and leaves behind darker, more complex organic material. That history explains why the object entered our solar system with a deep red color. Red coloration in comets is often linked to carbon-rich compounds that have been altered by long exposure to heat and radiation. After leaving its home system, 3I Atlas spent an extremely long time drifting through interstellar space. That environment is cold, dark, and quiet. During that time, any remaining surface activity would have shut down. Volatile materials would freeze in place, and a thin outer crust would gradually form. This crust does not need to be thick. Even a very shallow layer can seal in more active material underneath. When the object finally entered our solar system and began receiving sunlight again, that crust did not provide much protection. The renewed heating caused a rapid release of trapped gases and dust. That sudden reactivation explains the next major shift that observers recorded. After appearing red for weeks, the object erupted into a phase of strong activity and began glowing green, and at times even slightly blue. Green light in cometary objects is commonly associated with diatomic carbon and related molecules. These molecules fluoresce when exposed to sunlight, producing a vivid green glow. The fact that this phase appeared quickly suggests that the surface barrier was thin and easily disrupted. The object did not need prolonged heating to change its behavior. It responded almost immediately upon entering the inner solar system. Now that this eruptive phase appears to be ending, the object's appearance is changing once again. The green glow has faded, indicating that gas emission is decreasing. Dust is becoming the dominant contributor to the light we see. Dust reflects sunlight differently than gas, often producing warmer tones. In this case, the result is a clear golden color. This does not mean the object is cooling down. Instead, it suggests that the most volatile materials have already been released, and heavier particles are now shaping its visible signature. This transition is happening as 3I Atlas continues its motion across the sky. Over the coming weeks, it will move into the constellation Leo and remain on a path that carries it further inward, through the solar system and toward Jupiter. Jupiter's gravitational influence is strong, and objects that pass through this region often experience changes in their trajectory and internal stress. While 3I Atlas is not on a collision course with the planet, its approach places it in a dynamically active environment. That makes the timing of this golden phase especially noteworthy. To understand how scientists reach these conclusions, it helps to look at the earliest observations. The object was first detected on July 1st. Archival imagery from July 30th provides a clear baseline. Observations were taken across multiple wavelength bands, including green optical, red optical, and infrared. In the green optical images from that time, the object does not appear strongly green at all. Instead, it shows a muted yellow tone. This tells us that, at discovery, the green-emitting gases were not yet dominant. The red optical images from the same period show a much stronger signal. The object appears brightly red, and this red coloration remained consistent across many observations through the end of September. During that entire time, red light dominated its appearance. This consistency supports the idea that complex organic material was abundant at the surface, and that gas activity was relatively modest. Infrared observations from that early period add another important detail. In infrared light, the object appears bright, indicating that it was already active when it was first detected. Infrared emission is sensitive to heat and dust. Seeing a strong signal so early tells us that material was being released almost immediately after the object entered the inner solar system. This behavior aligns with the idea of a thin surface crust that could not hold back internal volatiles for long. Taken together, these observations paint a coherent picture. 3I Atlas arrived from interstellar space with a surface shaped by long-term heating around another star. It carried a thin outer layer that masked active material beneath. As soon as sunlight reached it again, that layer failed, leading to a rapid increase in activity and a dramatic color shift. The object moved from red to green and blue during peak gas release, and now into a gold-colored, dust-dominated phase. The fact that these transitions happened without the need for deep heating by our sun reinforces how fragile the object's surface structure likely is. It did not behave like a solid, inert body slowly warming up. Instead, it reacted quickly and dramatically. This sensitivity is what makes its current state so important. The golden glow may simply reflect a new balance between dust and gas, or it may point to internal changes that are still unfolding. What matters most is that the object continues to respond measurably to its environment, offering observable clues about the conditions it experienced long before it ever entered our solar system. To understand how this behavior developed, it helps to trace the observations back in time and examine how these changes first began to appear. As observations move closer to the present moment, the changes in 3i Atlas become easier to track in detail. Images taken on August 27th provide a clear snapshot of the object during an important transition phase. At that time, data were collected across multiple wavelength bands, including ultraviolet, green optical, red optical, and infrared. When these views are considered together, they show an object that was beginning to change, but had not yet fully shifted into its later, more active state. In the green optical band, 3i Atlas was starting to show a noticeable increase in green emission. The glow was still moderate, not yet dominant, but clearly stronger than in earlier observations. At the same time, the red optical band remained very strong. The object was still visibly red, confirming that complex organic material and dust were continuing to play a major role in shaping its appearance. The infrared data showed sustained activity, indicating ongoing release of material into the surrounding coma. The cloud of gas and dust that forms around an active comet-like body. These images were taken when the object was at a distance of about 2.59 astronomical units from the Sun. 1 astronomical unit is the average distance between Earth and the Sun. So this places the object well beyond Earth's orbit. This distance is scientifically important because it lies close to a boundary, often called the water-ice activation zone. Around 2.5 astronomical units, sunlight becomes strong enough for water ice to begin sublimating, meaning it turns directly from solid ice into gas. When this happens, it can dramatically change the behavior of an object like 3i Atlas. Before reaching this region, activity is usually driven by more volatile substances. These are materials that can become active at lower temperatures. In the case of 3i Atlas, early observations showed that carbon dioxide, cyanogen gas, known as CN, and significant amounts of nickel gas were present. These substances can escape from the surface at greater distances from the Sun than water ice. Their presence explains why the object was already active while still relatively far out in the solar system. The detection of nickel is especially notable. Nickel is a metal, and seeing it in gaseous form without a corresponding strong signal from iron is unusual. In most solar system comets, metals like nickel and iron tend to appear together, often released from dust grains as the comet heats up. The early presence of nickel in 3i Atlas suggests a surface chemistry shaped by intense heating in the past, likely during repeated close passes around its original star. This fits with the idea that the object spent a long time as a short-period comet in another planetary system before being ejected into interstellar space. As 3i Atlas approached the water-ice activation zone, its chemistry began to change. The August observations capture the object just before water-driven activity became significant. Soon after this point, In early September, astronomers observed a clear and sustained shift in color from red to green. This change marked a new phase. Water ice sublimation increases the release of certain molecules that fluoresce strongly in sunlight, producing green emission. The coma became richer in gas relative to dust, and the object's appearance responded accordingly. This red to green transition did not happen gradually over many months. It occurred over a relatively short period of time, reinforcing the idea that the surface layer was thin and easily altered. Once the conditions were right, the object responded quickly. This behavior is consistent with the body that has already been heavily processed in the past and no longer has thick, insulating layers of pristine ice. If we move forward in time by several weeks, the evolution becomes even more apparent. Images taken on November 26th, after the object passed perihelion, show another subtle but important change. Perihelion is the point in an object's orbit where it is closest to the Sun. After this point, heating begins to decrease, and the balance between gas and dust activity often shifts again. High-resolution observations from the Gemini North Telescope on that date reveal that 3I Atlas had developed a faint bluish tint in parts of its coma. There was still some green present, but it was no longer dominant. At the same time, warmer tones began to appear. This combination suggests that gas emission was starting to decline while dust was becoming more influential once again. The timing of this image is important because it appears to capture the object during the transition itself, rather than clearly before or after. Additional images from later dates support this interpretation. In those observations, the object appears as a mix of green and gold, with the gold component becoming stronger day by day. This gradual change indicates that the processes driving gas emission were winding down, while sunlight reflecting off dust particles was shaping the overall color. Dust does not fluoresce like gas. Instead, it reflects and scatters light, often producing yellow or golden tones. The Gemini North observations are particularly valuable because of their high spatial resolution. They allow scientists to study not just the color, but also the structure of the coma. Fine details in the distribution of material can reveal how evenly the object is releasing dust, whether jets are present, and how activity is evolving over time. In this case, the images show a relatively smooth coma, consistent with a general decline in gas-driven outbursts rather than a sudden explosive event. By December 10th, the change had become unmistakable. An image taken on that date shows 3I Atlas glowing with a strong golden color. The green emission that once defined its appearance had largely faded. This observation confirms that the object has now passed through 3 distinct color phases since entering the inner solar system. It began with a deep red appearance, shifted to green as gas activity increased, and has now transitioned into a gold, dust-dominated state. What makes this sequence especially compelling is that it is unfolding as the object moves into the constellation Leo. While the constellation itself does not affect the object physically, its position in the sky provides a useful reference point for observers around the world. The timing reinforces that these changes are part of a continuous evolution tied to distance from the Sun and the availability of different materials at the surface. Taken together, the observations from late August through December outline a coherent chemical and physical progression. Early activity driven by volatile compounds gave way to water ice sublimation, increasing gas emission and producing a green glow as the most easily released gases were exhausted and heating conditions changed after perihelion, dust became dominant again, leading to the golden appearance now being observed. Each phase builds logically on the one before it. That long sequence brings the object into a brief but especially valuable moment, where both its physical state and its observing geometry align. As the timeline moves closer to the present, 3I Atlas is entering a particularly important observational window. At the moment under discussion, the object is just 4 days away from its closest approach to Earth, with the date being December 15th. That closest approach will occur on December 19th. This timing is significant for 2 reasons. First, the distance to Earth will be at its minimum for this passage. Second, the night of December 19th coincides with a new moon. A new moon means that the sky will be naturally darker than usual. There will be little to no moonlight to wash out faint details. For astronomical observations, this creates near-optimal conditions, faint structures in the coma, subtle color differences, and low-contrast features become easier to detect when background light is minimized. This is especially important for an object like 3I Atlas, whose appearance is changing and whose brightness is modest compared to many familiar comets. During the early morning hours on December 19th, the object will be positioned fairly high above the horizon. This detail matters more than it might seem at first. When an object is low in the sky, its light passes through a thicker layer of Earth's atmosphere. That extra air introduces distortion, scattering, and color effects that can complicate interpretation. A higher position above the horizon reduces these issues, allowing observers to collect cleaner optical data. For anyone with access to telescopes or imaging equipment, this moment offers a rare chance to capture meaningful observations. Assuming local weather conditions allow for clear skies, however, the current interest in the object's golden appearance does not rest on a single observing session or a single set of images. The strength of the conclusion comes from consistency across many independent observations. When astronomers and experienced observers examine changes like this, they rely on patterns that repeat across different instruments, locations, and dates. This approach helps separate true physical changes from artifacts caused by cameras, filters, or atmospheric conditions. Additional images taken on December 14th provide an important piece of this larger pattern. In those observations, the object does not display a strong green color. While the image is not as vividly gold as some taken later, the absence of an obvious green component is telling. It suggests that the phase dominated by green-emitting gases has already diminished. In other words, this is not a temporary fluctuation seen by one observer, but part of a broader trend. More images taken shortly afterward reinforce this interpretation. In these newer observations, 3I Atlas appears to carry a mixed tone, showing hints of both green and gold. However, the balance has shifted. The gold component is becoming more prominent with each passing day. This gradual progression is important. It suggests a smooth physical transition rather than a sudden or chaotic event. Gas production is declining, while dust is becoming the dominant contributor to the object's visible appearance. One image captured by an observer in Italy illustrates this well. In that view, the object no longer exhibits the vivid green glow that once defined it. Instead, the color appears warmer and more muted, When this image is compared with data from earlier weeks, the direction of change becomes clear. The object is steadily moving away from gas-driven coloration and toward a dust-dominated state. This sequence of color changes reflects deeper physical processes tied to the object's history. When 3I Atlas was first detected, its coma was strongly red and dominated by dust. That red coloration remained remarkably stable for an extended period. Even as activity increased and more material was released into space, the overall color did not shift. This stability is notable. It indicates that, early on, the composition of the material being released was consistent and did not depend strongly on increasing sunlight. This behavior continued from the time of first detection through roughly the middle of September. During that interval, the object became progressively more active. More gas and dust entered the surrounding space, expanding the coma. Yet despite this increase in activity, the color remained red. This tells us that the initial phase of activity was driven by materials that did not significantly alter the object's optical signature. The key turning point occurred when 3I Atlas reached a distance of about 2.5 astronomical units from the Sun. This distance marks an important physical boundary. At roughly this range, sunlight becomes strong enough to efficiently activate water ice. Water ice does not simply melt. In the vacuum of space, it sublimates, turning directly from solid ice into gas. When this happens, it can dramatically change the chemistry and appearance of a comet-like object. Before reaching this water activation zone, activity was driven mainly by more volatile compounds. These include carbon dioxide and cyanogen gas, often abbreviated as CN. Such substances can sublimate at lower temperatures, which is why the object showed activity even while still relatively far from the Sun. In addition to these gases, observations also revealed significant amounts of nickel in gaseous form, an unusual finding that points to a heavily processed surface. Despite the growing activity from these volatiles, the object's color remained stable. Gas and dust production increased, but the balance between them did not change enough to alter the visible appearance. This suggests that the surface layers being exposed were chemically similar and that no major transition had yet been triggered. Once the object crossed the 2.5 astronomical unit threshold in early September, conditions changed. Water-driven sublimation began to contribute significantly to the coma. This introduced new molecules that fluoresce when exposed to sunlight. The result was a noticeable shift from red to green. This transition marked the most active and visually striking phase of the object's evolution. Importantly, this color change did not unfold slowly over many months. It occurred over a relatively short period. That rapid response suggests that the surface layer was thin and easily altered. The object did not require prolonged heating to reach a new state. Once the right conditions were met, the chemistry and appearance shifted quickly. Now, as 3I Atlas continues past perihelion and moves toward its closest approach to Earth, that gas-rich phase is coming to an end. The most volatile materials have already been released. The green glow is fading. What remains is a coma, increasingly shaped by dust. Unlike the earlier dust-dominated phase, this dust now reflects sunlight in a way that produces a golden hue rather than deep red. This difference likely reflects changes in grain size, surface texture, or composition of the material now being released. From the first observations through mid-September, the object's color remained stable even as activity increased. That stability, followed by sharp transitions at specific distances, provides important clues about its structure and history. It suggests a body with a thin surface layer, shaped by extensive thermal processing long before it entered our solar system. Now responding quickly and predictably as different materials become active and then are exhausted. Seen in that context, the behavior of 3I Atlas stands out even more clearly when placed alongside other interstellar visitors. When scientists compare 3I Atlas to earlier interstellar objects, the differences become apparent almost immediately. The first known interstellar visitor, often referenced as Oumuamua, appeared extremely dark, with a surface that reflected very little light. Another, later object behaved much more like a familiar solar system comet, showing properties that fit comfortably within existing expectations. 3I Atlas does not align cleanly with either case. From the beginning, it has appeared redder than previous interstellar objects, and its behavior has been less predictable. That alone places it in a separate category, and the chemical signals observed in its coma sharpen that contrast further. One of the most striking features has been the early appearance of nickel emission. This nickel signal emerged clearly and strongly in spectroscopic data, and it did so without a corresponding increase in iron emission. This is not a subtle effect. The spectroscopic measurements show a pronounced rise in nickel-related lines, while iron remains largely absent. For researchers following the object closely, this pattern has been consistent and difficult to dismiss as noise or observational error. It is important to clarify what this does and does not mean. The absence of iron emission in the coma does not mean that the nucleus of 3I Atlas contains no iron. Astronomers are not directly observing the solid nucleus itself. What telescopes detect is the coma, the cloud of gas and dust released from the surface and then altered by sunlight. Once material enters the coma, it can become ionized, meaning its atoms lose electrons and emit light at specific wavelengths. The data reflect what reaches this surrounding cloud, not what remains locked inside the core. The key question, then, is why nickel is reaching the coma while iron is not. This points to a selective transport process rather than a simple absence of material. One explanation that fits both the observations and known chemistry involves compounds called metal carbonyls. These are molecules in which a metal atom is bound to carbon monoxide. Both nickel carbonyl and iron carbonyl can form under certain conditions, and both are capable of becoming volatile, meaning they can transition into gas at relatively low temperatures. However, there is an important difference between the two. Nickel carbonyl is more chemically stable than iron carbonyl. Iron carbonyl is highly reactive. In an environment where water or other reactive compounds are present, iron carbonyl is more likely to break apart or react before it can escape the nucleus. Nickel carbonyl, being more stable, can survive long enough to migrate outward. Once it reaches the coma, exposure to solar radiation causes it to break down, releasing free nickel atoms. These atoms then produce the nickel emission lines seen so clearly in spectroscopic data. This mechanism explains why nickel can appear strongly in the coma without iron doing the same. It also explains why the nickel signal increased rapidly once activity began. As soon as conditions allowed these compounds to volatilize, nickel carbonyl could move efficiently from the nucleus into space. The result is a sharp spike in nickel emission that stands out against expectations based on solar system comets. Alongside nickel, observers also detected significant amounts of cyanide and cyanogen gas. These molecules are commonly abbreviated as CN in scientific contexts and are often associated with cometary activity. Their presence adds another layer of information. Cyanogen gas typically becomes visible when organic-rich material is exposed to sunlight. Seeing it emerge soon after activity increased reinforces the idea that 3I Atlas carries a substantial load of carbon-based compounds taken together. These chemical signals act as clues to the object's past. They suggest a history that involved intense heating, followed by long exposure to the interstellar environment. Based on the full set of observations, the most consistent scenario is that 3I Atlas once behaved as a short-period comet around its original star. Short-period comets are objects that orbit their star frequently, passing close to it again and again over long periods of time. Repeated close passes would have subjected the object to strong stellar radiation over hundreds or even thousands of orbits. This energy would have stripped away many volatile and fragile compounds. Exotic ices and easily altered materials would have been lost early. What remained would be a heavily processed nucleus, dominated by more resilient components. In effect, the object would have been baked down to a relatively bare core compared to comets that spend most of their lives far from their stars. At some point, gravitational interactions within that original star system likely altered its trajectory. A close encounter with a massive planet or another star could have provided the energy needed to eject it entirely. Once expelled, 3I Atlas would have entered interstellar space, beginning a journey that may have lasted millions or even billions of years. Interstellar space is not truly empty. While matter there is extremely sparse, it contains the products of countless stellar events. When stars explode as supernovae, they create and distribute heavy elements throughout the galaxy. Over long timescales, dust grains, atoms, and molecules drift through this environment. An object traveling through interstellar space can slowly accumulate material on its surface. Even though the density is very low, during this long journey, 3I Atlas likely collected new material. This includes water, various compounds, and complex organic molecules. These additions would not form thick layers, but over immense timescales, they can create a coating that is chemically distinct from the original nucleus. This process helps explain why the object appears rich in organics despite having been heavily processed earlier in its life. The red coloration seen when the object was first detected is a strong indicator of organic-rich dust. Similar red tones are observed in certain distant solar system bodies, such as trans-Neptunian objects and D-type asteroids. These bodies are known to contain complex organic compounds. Laboratory studies have shown that such materials can participate in chemical reactions that produce amino acids and nucleotide-based structures, the basic components involved in biological chemistry. While this does not imply life, it highlights the richness of the chemistry involved. In earlier discussions, some researchers have explored the idea that objects like 3I Atlas could act as carriers of complex chemistry across star systems. This concept is sometimes described as an interstellar seeding process. In this context, it refers to the transport of organic material, not living organisms. Such accumulation would be a one-time process during the interstellar journey. unless the object were to survive and be ejected again into deep space. As 3I Atlas approached our Sun, the consequences of this accumulated material became apparent. Unlike long-period comets from the outer solar system, it did not possess a large, fresh reservoir of volatile ices. Instead, it carried a limited supply gathered during its interstellar passage. When sunlight began heating the surface, that supply activated relatively quickly and intensely. The change in energy input was dramatic. Near its closest approach to the Sun, the object received roughly 735 watts per square meter of solar energy in interstellar space. By contrast, the background light provides on the order of 10 to the -7 to 10 to the -8 watts per square meter. This represents an increase of roughly 10 orders of magnitude in received energy. Such a jump is extreme. Materials that were stable for eons in deep space suddenly found themselves exposed to intense radiation. This sudden influx of energy explains the rapid awakening observed earlier. Organic compounds and volatile materials began to sublimate and break apart. Gas production surged, driving the transition from a red, dust-dominated coma to a green, gas-rich one. This phase marked the peak of chemical activity, when the interstellar coating was being stripped away. Once that reservoir was exhausted, conditions changed again, with fewer volatile compounds left to fuel gas emission. The coma began returning to a dust-dominated state. However, the dust being released now was not identical to what had dominated earlier. Many of the organic compounds responsible for the deep red coloration had already been volatilized and carried away with the gas and dust during the active phase. As a result, the remaining material reflects sunlight differently. The balance of particle sizes, compositions, and surface coatings produces a warmer, golden appearance rather than the original red. This final shift completes the sequence observed so far. 3I Atlas began as a red object shaped by long-term processing and organic accumulation, erupted into a green, gas-rich phase when exposed to intense solar energy, and is now settling into a gold-colored, dust-dominated state as that temporary supply of volatile material is depleted. Taken together, this sequence provides the framework needed to assess the object's past, even if that assessment must remain provisional based on everything that has been observed so far. This remains the most plausible history for 3I Atlas. It is important to be clear about the limits of certainty. No single dataset can provide a definitive reconstruction of its past. However, when the physical behavior, the timing of activity, and the chemical signatures are considered together, they form a coherent picture. The observations are consistent with one another, and they align with what is already known about how cometary material responds to heating and long exposure to space. This is why continued observation matters. Patterns only become meaningful when they persist over time and appear across independent measurements. In the case of 3I Atlas, the progression from a red, dust-dominated appearance to a green, gas-rich phase, and now toward a gold-colored coma, follows a sequence that has precedent. Even if the object itself is unusual, the chemistry supports this interpretation, rather than contradicting it. This makes the next phase especially worth watching. When a similar color transition occurred in the solar system, comet designated C2025K1 Atlas, The shift toward a gold-dominated appearance was followed very shortly by fragmentation. That does not establish a rule, and it does not mean that the same outcome must occur here. However, it does provide a relevant comparison. When color changes coincide with declining gas activity and increasing dust dominance, it can indicate structural stress or changes within the nucleus. For an object that has already been heavily processed in the past, those signals carry additional weight. Timing plays a central role in what can be learned next. 3I Atlas is approaching its closest distance to Earth in just 4 days. On December 19th, this moment represents the point at which the object will be easiest to study from our planet. Not because it will suddenly become bright, but because geometry and lighting conditions are especially favorable. Understanding where the object is located in the sky during this period helps observers plan and interpret their observations. To visualize this, astronomers often rely on sky simulation software that shows the night sky from Earth's perspective. These tools allow the ecliptic plane to be displayed, along with the positions of stars, planets, and moving objects. The ecliptic plane is the plane of Earth's orbit around the Sun, and most objects in the solar system move close to it. Seeing 3I Atlas relative to this plane helps place its motion in context. When the simulation is set to the current date and then advanced forward in time, the object becomes visible during the early morning hours, around 4 o'clock in the morning local time. 3I Atlas rises well above the horizon. At this time, it can be located as it moves from the constellation Virgo into the constellation Leo. This motion is gradual but clear when tracked night by night. While constellations have no physical influence on the object, they serve as stable reference markers on the sky. They allow observers in different locations to describe positions consistently. In this case, noting the transition from Virgo into Leo helps establish where the object is relative to familiar star patterns and confirms that observations taken on different nights are aligned in time as the date advances from December 16th toward December 19th. The position of the moon becomes increasingly important. On December 16th, the moon is still separated from the sun and visible in the sky. As time moves forward, the moon approaches alignment with the sun. By December 19th, the moon and the sun occupy nearly the same position in the sky. This alignment defines the new moon phase. During a new moon, the moon does not illuminate the night sky. This absence of moonlight significantly improves observing conditions for faint objects. Background brightness is reduced, contrast increases, and subtle features become easier to detect. For an object like 3I Atlas, which is not exceptionally bright, this reduction in sky glow can make a substantial difference. At the same time, simulations show that the object remains well positioned in the sky during the early morning hours on December 19th. It is not lost near the horizon, nor is it overwhelmed by twilight during the optimal observing window. This combination of factors makes the closest approach particularly valuable from an observational standpoint. It is also important to note that the object has already passed perihelion. Since that point, it has begun to dim slightly. This behavior is expected. As distance from the sun increases, the energy driving sublimation decreases, and gas production tends to decline. However, dimming does not mean that the object has become uninteresting. In many cases, The period after peak activity reveals structural details that are harder to see when strong outgassing dominates. During this quieter phase, the shape and extent of the coma can be studied more clearly. Changes in brightness can be tracked with greater precision. Any signs of uneven dust release or subtle fragmentation become easier to identify when the overwhelming glare of gas emission has faded. This makes the current window especially valuable for understanding how the object is settling after its most active period. Looking further ahead, the outlook becomes more challenging. As the calendar moves into January, and then into February and March of 2026, 3I Atlas is expected to continue fading. Its distance from Earth will increase, and the decreasing solar input will further reduce activity. At the same time, the object will move closer to Jupiter's region of influence. While it is not on a collision course, the gravitational environment becomes more complex. There is also the possibility, though not a certainty, that structural changes could occur. Fragmentation remains an open question. Given the object's unusual composition, thin surface layers, and history of intense processing, it is not unreasonable to consider whether or not such changes occur. The observations gathered during this closest approach will serve as a baseline for comparison in the months that follow. At present, 3I Atlas occupies a region of the sky between Virgo and Leo. This position marks a clear stage in its journey. It is a location that can be consistently identified and revisited across multiple nights, allowing observations to be compared directly. As it continues moving through this region, the data collected now will define how this interstellar object looks and behaves as it transitions away from peak activity and into a more subdued, dust-dominated phase. At this stage, the available evidence points toward interstellar object 3I Atlas entering a phase in which its coma appears predominantly golden. Multiple observations collected over recent nights show a clear reduction in the green emission that once dominated its appearance, accompanied by warmer tones that are becoming more persistent. This trend is noticeable across different observers and instruments, which gives it weight. Even so, the conclusion remains provisional. In astronomy, especially when studying faint and rapidly evolving objects, caution is essential. Color is one of the most easily misinterpreted properties in observational data. A single image can be influenced by atmospheric transparency, seeing conditions, camera sensitivity, filter bandwidth, and even post-processing choices. For this reason, astronomers rarely treat any color change as definitive until it is confirmed repeatedly. What matters most is whether the same color balance appears night after night, under different conditions, and when analyzed using consistent methods in the coming days. Additional observations will help clarify whether the golden appearance of 3I Atlas represents a stable physical state or a temporary fluctuation. If the color remains consistent across new datasets, confidence will grow that a genuine transition has occurred. If, instead, the color oscillates between green and gold, that would indicate an ongoing competition between gas emission and dust scattering rather than a completed shift. To understand why this distinction matters, it helps to consider how color is produced in comet-like objects. The nucleus itself is far too small and faint to observe directly. What telescopes record is the coma, a diffuse cloud of material released from the surface. The coma is composed of gas molecules and dust grains, each contributing light in different ways. Gas molecules emit light at specific wavelengths when they are excited by sunlight. These emissions are narrow and strong, producing distinctive colors. Green emission, for example, is commonly associated with molecules such as diatomic carbon and related species. Blue tones can arise from ionized gases. When gas production is high, these emissions dominate the visual appearance of the object. Dust behaves very differently. Dust grains do not emit light at specific wavelengths. Instead, they reflect and scatter sunlight across a broad range of wavelengths. The color produced by dust depends on the size of the grains, their surface composition, and how they interact with light. Fine dust can appear neutral or slightly red, while larger or more processed grains can produce yellow or golden tones. In the case of 3I Atlas, earlier observations clearly showed a gas-rich phase. After crossing the water activation boundary near 2.5 astronomical units from the Sun, gas production increased sharply. The coma became dominated by green emission, indicating strong sublimation of volatile compounds. This phase marked the peak of chemical activity as the object responded to intense solar heating. As the object passed perihelion, the situation began to change. Solar energy input gradually decreased, and the most easily released gases were depleted. When gas production declines, the relative contribution of dust increases. Even if dust release remains steady or slowly decreases, the visual result is a shift away from narrow emission colors toward broader, warmer tones. The golden appearance now being reported fits this expected progression. Multiple images show that green emission has weakened significantly. At the same time, the overall brightness of the coma is increasingly shaped by reflected sunlight rather than fluorescent gas emission. This suggests that the object is entering a dust-dominated phase. However, interstellar objects introduce additional complexity. Unlike many solar system comets, 3I Atlas likely arrived with a limited and uneven distribution of volatile material. Its surface was shaped by prolonged heating around another star, followed by a long journey through interstellar space. These factors mean that activity may not decline smoothly or uniformly. Localized pockets of material could still become active, temporarily altering the balance between gas and dust. This is why repeated observation is so important during this period. The days around closest approach to Earth provide especially good conditions for collecting high-quality data. With the moon absent from the night sky, background brightness is minimized. This improves contrast and makes subtle color differences easier to detect. It also reduces the risk that faint green emission could be hidden or exaggerated by sky glow. High signal-to-noise observations taken under these conditions allow astronomers to compare brightness levels in different wavelength bands more reliably. If measurements show that light in green-sensitive filters continues to decline, while broadband brightness remains steady, that would support the conclusion that dust is now the dominant contributor. If green emission resurges, that would point to renewed gas release. Stability is often more informative than dramatic change. If the golden coloration persists over several nights with little variation, it suggests that the object has settled into a new equilibrium. This would indicate that the major phase of volatile-driven activity has ended, and that the remaining material is being released more slowly and uniformly. Such an outcome would be consistent with the idea that the temporary layer of material accumulated during the object's interstellar journey has largely been exhausted. Once that layer is gone, the object behaves more like a dust-rich body with limited remaining volatiles. The golden color would then be a natural consequence of the physical properties of the dust now dominating the coma. If the color continues to evolve, that information will be just as valuable. A gradual fading toward a more neutral tone could indicate further depletion of fine dust. A partial return of green emission could signal exposure of a previously insulated region of the nucleus. Each possibility provides insight into the internal structure and remaining inventory of material. For now, the most scientifically sound position is restraint. The evidence points toward a gold-dominated phase, but confirmation requires additional data over the next several days. As more observations are collected and compared, the picture will either solidify or reveal new complexity. This careful, methodical process is how fleeting impressions are transformed into reliable understanding, and it will determine whether the golden appearance of 3I Atlas becomes a defining feature of its passage through the inner solar system. As this observational window continues, the coming nights will play a decisive role in refining what can be said with confidence about 3I Atlas. The object is no longer undergoing rapid, dramatic change, and that in itself is informative. When activity slows, short-lived effects fade, and longer-term physical trends become easier to isolate. This is often when the most reliable conclusions can be drawn. If the golden coloration remains consistent through repeated observations, it will suggest that the object has reached a relatively stable phase, dominated by dust scattering rather than gas emission. That stability would mark a clear endpoint to the most chemically active stage of its encounter with the inner solar system. In that case, the recent evolution would appear not as a sudden anomaly, but as the final step in a sequence driven by energy input, material availability, and surface history. It is also worth noting that absence of change is itself a meaningful result. If no renewed gas emission appears, and no sudden structural disruption occurs, that outcome places limits on how much volatile material remains accessible near the surface. It would indicate that most easily mobilized compounds have already been released, leaving behind a more inert outer layer that responds slowly to further heating. At the same time, any deviation from this pattern will be equally valuable. A localized increase in activity, even a modest one, would suggest internal heterogeneity and uneven layering within the nucleus. Such behavior would provide insight into how material was deposited during the object's interstellar journey and how thoroughly earlier thermal processing reshaped its structure. What makes this period especially important is that it represents the last phase in which detailed study is feasible at relatively close range. As distance increases in the months ahead, signal strength will drop, and interpretations will rely increasingly on fewer data points. The observations collected now will therefore define the reference frame against which all later measurements are compared. In that sense, 3I Atlas is offering a rare opportunity, not simply to observe an interstellar visitor, but to document, with clarity and restraint, how such an object settles after intense exposure to a new star. Whether the golden appearance proves to be a lasting state or a transient one, the process of confirming it will deepen understanding of how material formed around one star responds when introduced to another.